We're going to talk about E, the big famous constant E. Okay, it's one of the famous mathematical constants, one of the most important. It goes along with pi and, I don't know, golden ratio and square root of 2. There are constants in maths that are the most important constants. And E is one of those constants. So E is an irrational number and it's equal to 2.718281828 something something something. The problem with E is it's not defined by geometry. Now pi is something that's defined by geometry, right? It's the ratio of a circle circumference and its diameter, and it's something the ancient Greeks knew about. And a lot of mathematical constants go back to the ancient Greeks, but E is different. E is not based on a shape. It's not based on geometry. It's a mathematical constant that is related to growth and rate of change. But why is it related to growth and rate of change? So let's look at the original problem where E was first used. So we're going to go back to the 17th century, and this is Jacob Bernoulli, and he was interested in compound interest, so earning interest on your money. So imagine you've got £1 in the bank, and you have a very generous bank, and they're going to offer you 100% interest every year. Wow, thanks a lot, bank. So 100% interest, so it means after 1 year, you'll have £2. So you've earned £1 interest, and you've got your original pound. So you now have £2. What if I offered you instead 50% interest every 6 months? Now, is that better or worse? Well, let's think about it. Okay, you're starting with £1, and then I'm going to offer you 50% interest every 6 months. So after 6 months, you now have £1.50. And then you wait another 6 months, and you're earning 50% interest on your total, which is another 75p. And then you add that on to what you had, so it's £2.25. Better. It's better. So what happens if I do this more regularly? What if I do it every month? I offer you 1/12 interest every month. Is that better? So let's think about that. So after the first month, it's going to be multiplied by this. 1 plus 1/12. So 1/12, that's your interest, and then you're adding that onto the original pound that you've got. So you do that, that's your first month. And then for your second month, you take that and multiply it again by the same value. And then your third month, you would multiply it again and again. You actually do that 12 times in a year. So in a year, you would raise that to the power 12, and you would get £2.61. So it's actually better. In fact, the more frequent your interest is, the better the result. Let's start with every week. Okay, so if we do it for every week, how much better is that? Okay, what I'm saying is you're earning 1/52 interest every week, and then after the end of the year, you've got 52 weeks, and you would have £2.69. So it's getting better and better and better. In general, you might be able to see a pattern happening here. In general, it would look like this. You'd be multiplying by 1 plus 1/n to the power n. Hopefully you can see that pattern happening. So here n is equal to 12 if you do it every month, 52 if you do it every week. If you did it every day, it'd be £1 multiplied by 1/365 to the power 365, and that's equal to £2.71. And so it would get better if you did it every second or every nanosecond. What if I could do it continuously? Every instant I'm earning interest, continuous interest. What does that look like? That means if I take this formula here, 1 plus 1/n to the n, I'm going to n tend to infinity. That would be continuous interest. Now, what is that? What is that value? And that's what Bernoulli wanted to know. He didn't work it out. He knew it was between 2 and 3. So 50 years later, Euler worked it out. Euler, he works everything out.
Him or Gauss?
Yeah, it's either Euler or Gauss. Say Euler or Gauss, you're probably going to be right. And the value was 2.71828282845 and so on.
We were pretty close when we were doing it daily, weren't we? It was already 271 at daily.
You're right. We're getting closer, weren't we? We're getting closer and closer to this value. So already we're quite close to it. If you did it forever, though, of course, you would have this irrational number. Now, Euler called this E. He didn't name it after himself, although it is now known as the Euler constant.
Why do you call it E then?
It was just a letter. You know, he might have used A, B, C, and D already for something else, right? So you use the next one.
Bit of a coincidence.
It's a lovely coincidence. I fully believe that he's not being a jerk here, naming it after himself, but it's a lovely coincidence that it's E for Euler's number.
Would you have called it G if you discovered it?
I would not have called it G. No, I would have hoped somebody else would have called it G, and then I would have accepted that. Euler proved that this was irrational. He found a formula for E, which was a new formula, not this one here, a different formula, and it showed that it was irrational. I'll quickly show you that. He found that E was equal to 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 1 plus 1 over 6 plus, and this goes on forever. This is a fraction that goes on forever, continuous fraction, but you can see it goes on forever because there's a pattern, and that pattern does hold. You've got 2, 1, 1, 4, 1, 1, 6, 1, 1, 8. So you can see that pattern goes on forever, and if the fraction goes on forever, it means it's an irrational number. If it didn't go on forever, it would terminate. And if it terminates, you can write it as a fraction. And he also worked out the value for E. He did it up to 18 decimal places. To do that, he had a different formula to do that. I'll show you that one. So this time, he worked out that E was equal to 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial. And this is something that's going on forever. It's a nice formula. If you're happy with factorials, factorials means you're multiplying all the numbers up to that value. So if it was 4 factorial, it'd be 4 times 3 times 2 times 1. Okay, why is E a big deal? It's because E is the natural language of growth. And I'll show you why. Okay, let's draw a graph. Y equals e to the x. So we're taking powers of E. So here at 0, this would cross at 1. So if you took a point on this graph, right, the value at that point is e to the power x. And this is why it's important. The gradient at that point, the gradient of the curve at that point is e to the x. And the area under the curve, which means the area under the curve all the way down to minus infinity, is e to the x. And it's the only function that has that property. So it has the same value, gradient, and area at every point along the line. So at 1, the value is e, because it's e to the power 1. The value is 2.718, the gradient is 2.718, and the area under the curve is 2.718. The reason this is important then, because it's unique in having this property as well, it becomes the natural language of calculus. And calculus is the maths of rate of change and growth and areas, maths like that. And if you're interested in those things, if you write it in terms of E, then the maths becomes much simpler. Because if you don't write it in terms of E, you get lots of nasty constants, and the maths is really messy. If you're trying to deliberately avoid using E, you're making it hard for yourself. It's the natural language of growth. And of course, E is famous for bringing together all the famous mathematical constants with this formula, Euler's formula, which is e to the I pi plus 1 equals 0. So there we have all the big mathematical constants in one formula brought together. We've got e, we've got I, square root of minus 1, we've got pi, of course, we've got 1 and 0, and they bring them all together in one formula, which is often voted as the most beautiful formula in mathematics.